Hello, in this lecture we answer on two questions. In the first question, we find out the area of this circle that is inscribed by trapezoid ABCD. And in the second question, we find out the length of this line segment QB that is equal to x. So we start with the first question. In the drawing we have trapezoid ABCD. The definition of a trapezoid is quadrilateral with one pair of parallel sides. So a trapezoid ABCD, side AD is parallel to side BC. Okay, so we have a circle that is inscribed by trapezoid ABCD. The length of this line segment AM is A. Line segment MB equals to B units in its length. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. And we define the point of tendency of this standard AD with this circle. This point is point P. Likewise, we define the point of tendency of tangent BC with this circle. This point is point Q. Here we can implement all two. So I'll repeat quickly on all two. So according to all two, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle. This is a common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this one, all two, they are equal to each other. That is to say, PA equals to PB. So we can actually implement all two in our drawing. In our drawing, we have, this is the common external point A. From this common external point A, we have two tangents to this circle, tangent AP and tangent AM. And according to all two, they are equal to each other. That is to say, AP equals to AM. But AM equals to A, according to what is given in the equation. Therefore, AP must be also equal to A units in its length, according to all two. So, AP equals to A. Likewise, we'll focus on this common external point B. From this common external point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to all two, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B, according to what is given as the question. Therefore, BQ must be also equal to B, according to all two. So this is tangent BQ, that is equal to B units in its length. In the next step, we define the radius of this circle as x, and we join points O and Q together by a straight line. Point O is the center of the circle. Point Q is a point on the circle itself, therefore OQ is the radius of this circle that is equals to x according to our definition. And because of the fact that the radius of Q that is equal to x, the radius of Q is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will join points O and P together by straight line. OP is of course the radius of this circle is equal to x, and because of the fact that the radius OP is going to point P, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is going to the point of tendency, then tangent AP will be perpendicular to the radius PO. If tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. In the next step, we will do a construction. That is to say, from this point, point A, we will do perpendicular on BC. Again, from point A, we will do perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we're going to do those two angles. Those two angles are defined as one-sided internal angles, and they are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid. In trapezoid ABCD, we have one pair of parallel sides. This trapezoid ABCD, side AD is parallel to side BC. So those two one-sided internal angles are located between the parallel lines AD and BC. And therefore, according to rule 17, the sum of two one-sided internal angles that are located between parallel lines is equal to 180 degrees. I repeat again on rule 17. According to rule 17, the sum of one-sided internal angles between two parallel lines is equal to 180 degrees. In the long run, we have line A that is parallel to line B. The red line C intersects with those two lines A and B at those 2 points. Those are angles alpha and beta, and they are defined as one-sided internal angles. And according to this rule, rule 17, the sum of those two one-sided internal angles that are located between the parallel lines A and B is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So actually, we have already implemented rule 17 in our drawing. In our drawing, we have those two one-sided internal angles that are located between the parallel lines AD and BC. And according to rule 17, the sum of those two one-sided internal angles is equal to 180 degrees. This angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say, from this point O, that is the center of this circle, we will do perpendicular on AN. Again, from point O, we will do perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we will derive the small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, we focus on the law of small quadrilateral TOQL. Inside this small quadrilateral, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So if we found out that angle POQ, the size of the big angle POQ is 180 degrees. So I write it down. Because 90 degrees plus 90 degrees, it is 180 degrees. So the size of the big angle POQ is 180 degrees. So I write it down. Angle POQ equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size is defined as a straight line. Therefore, line segment POQ is a straight line. Actually here, I didn't draw the line segment OQ correctly, so it doesn't look like a straight line, but it is actually a straight line. Okay? Actually, line segment OQ should be drawn smaller to the small right side, and in this way it will be POQ will be a straight line. So POQ equals, it is a straight line, a line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. PQ is a straight line. So inside the shape APQN, this shape APQN consists of 4 sides. 1, 2, 3, 4. So I write down shape APQN consists of 4 sides. Therefore, shape APQN is a quadrilateral. Shape APQN is a quadrilateral. And we already found out that quadrilateral APQN has 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be its rectangle if not a square. So we relate to quadrilateral APQN as a rectangle because it has 4 right angles. So I write it down. This is the big quadrilateral APQN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side NQ. But AP is A, therefore NQ must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x. Therefore, AN must be also equal to 2x units in its length. What is the length of the missing line segment BN? BN in total equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So I write it down. BN equals to BQ minus NQ. So BN in total equals to BQ is B according to rule 2 minus NQ. NQ is A. So in total BN equals to B minus A units in its length. BN equals to A minus B units. In the next step, I'll copy the right triangle A and B. This right triangle A and B in a new page. We'll implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AB equals to A plus B, the hypotenuse. BN equals to A minus B units in its length. And side AN equals to 2x units in its length. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle ABN that according from the original drawing. In this right triangle ABN, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. So I write it down. AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared. 2x squared is 4x squared, plus BN squared. BN is A minus B, therefore BN squared is A minus B squared. So in total we found out that A plus B squared equals to 4x squared plus A minus B squared. Here we'll open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus A minus B squared. A minus B squared equals to A squared plus B squared plus 2 times A times B. So here we have A squared on both sides of this equation, so A squared will get cancelled. We have also B squared on both sides of the equation, so B squared also will get cancelled. After we cancel those two expressions, in this side of the equation we have to leave 2AB. On the other side of the equation we have 4x squared minus 2AB. So here we add 2AB to this equation, and we get that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. So here we divide this equation by 4, and we get that 4AB over 4 is AB, equals to 4x squared over 4 is x squared. So in total we should find out that AB equals to x squared. Repeat again, we should find out that AB equals to x squared. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. I repeat again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle. The radius of this circle is x squared. So in total we should find out that the area of this circle equals to pi x squared. But we just find out that x squared equals to AB. So we substitute x squared here by AB, and we get that the area of the circle equals to pi times AB. So we can find out that the area of the circle is equal to pi times AB square units. And that is the answer to the question. Repeat again, we actually found out that the area of this circle is equal to pi times AB square units. So we finish with the first question. In the next step, I will present you the second question and we'll solve the second question of this lecture. Our mission in the second question is to find out the length of this line segment QB that is equal to x. We have to find out the value of x. So in the drawing we have a semicircle. We know that AB equals to 30 units in its length. Again, AB equals to 30 units in its length. AB is the diameter of this semicircle, so we know that the diameter of this semicircle equals to 30 units. In addition, we know that this is called PA, that is equals to 10 units in its length. This is called PQ, that is also equals to 10 units in its length. And this is called QB, that is equal to x units. And our mission is to find out the length of called QB that is equal to x. We have to find out the value of x. Because of the fact that the diameter of this semicircle is equal to 30 units, the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So the radius of this semicircle equals to 15 units. So I write it down. The radius of this semicircle is equal to 15 units in its length. We define the center of this semicircle. This point is point O. So point O is the center of the semicircle, point A is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, OA is the radius of this semicircle. This is equal to 15 units in its length. Likewise, OB is also the radius of this semicircle. This is equal to 15 units in its length. In the next step, we join points O and P together by a straight line. Point O is the center of the semicircle, point P is the point on the semicircle as well. Therefore, OP is the radius of this semicircle. That's equal to 15 units in its length. In the next step, we will do a construction. That is to say, we will complete this semicircle to a circle. And we will extend the radius PO by straight line until it touches the circle. And we define the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle, that's equal to 15 units in its length. In the next step, we join points B and M together by a straight line. Those two angles are defined as vertex angles, so we know that vertex angles are equal to each other. So if the side of this vertex angle is theta, then the side of this vertex angles must be also equal to theta because they are equal to each other. In the next step, we prove that triangle APO can point to this triangle MOB. We prove that those two triangles can go into each other. So if you know, so we prove that this triangle APO can go into this triangle MOB. So why those two triangles can go into each other? First of all, side PO of triangle AOP is equal to side OM of triangle OMB. They are both the radii of the circle, therefore they are equal to each other. So I write it down. PO equals to OM equals to 15. Repeat again. Side PO of triangle APO is equal to side OM of triangle MOB. They are both the radii of the circle that is equal to 15 units, therefore they are equal to each other. In addition, those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So this is angle AOP, and it is equal to this angle, that is actually angle MOB. So repeat again, angle AOP triangle APO equals to angle MOB triangle MOB. They are defined as vertex angles, so we know that vertex angles are equal to each other. And finally, side AO of triangle APO is equal to side OB of triangle MOB. They are both the radii of the circle, that is equal to 15 units, therefore they are equal to each other. So I write it down. AO equals to OB equals to 15. So repeat again. Side AO of triangle APO equals to side OB of triangle MOB. They are both the radii of the circle that is equal to 15, therefore they are equal to each other. So actually proved that this triangle APO can go into this triangle MOB according to side angle side rule. That is to say, we actually prove that those two sides and the angle that included between those two sides in triangle APO are correspondingly equal to those two sides and the angle that included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rules. So I write it down. We actually prove that triangle APO congruent, this is the sign of congruent, to triangle MOB according to side angle side rule. And for the fact that those two triangles can go into each other, we will derive that side AP in triangle APO is equal to side MB in triangle OMB. I'll write it down. AP equals to MB. Those two sides are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go to each other, therefore the two corresponding sides, that is to say AP and MB, must be also equal to each other. But AP equals to 10 units in its length according to what is given us the question. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we will derive that MB is also equal to 10 units in its length. MB equals to 10 units. Side MB equals to 10 units in its length. Chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of this circle. So PM is the diameter of this circle. So I'll copy this semicircle with the diameter PM, and we will analyze this semicircle. Okay. So really, this is the semicircle with the diameter PM that I copied from the original drawing. We know that PQ equals to 10 units, BM also equals to 10 units, and point O is the center of this semicircle. In the next step, we will extend PQ and MB by straight line until they intersect with each other. So here, this is their intersection point, or their touching point. We will define the touching point of the extended PQ and BA and MB. This point is point E. Actually, we have the rule that if we extend two line segments that are equal to each other until they intersect with each other, then the new line segment that will be created must be also equal to each other. That is to say, after we extended PQ and MB, the new line segments must be also equal to each other. That is to say, PE is equal to ME. PE equals to ME. Actually, by doing this construction, we created here triangle PEM. And we know that in this triangle PEM, side PE equals to side EM. And therefore, triangle EPM is an isosceles triangle, and actually we know that those two angles are equal to each other in an isosceles triangle. Anyway, we'll prove that those two angles are equal to each other. According to the rule that in front of equal sides in the triangles are equal angles. In front of this side EP we have this angle, and in front of this side EM we have this angle, and those two angles are located in front of those two equal sides, and therefore they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. Okay? So in the next step, we will complete this semicircle to a circle. So completed the semicircle to a circle. So in the drawing we have quadrilateral PQBM. This is quadrilateral PQBM that is described by this circle. And we have the rule that says that if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So in the drawing we have quadrilateral ABCD that is inscribed by this circle, and those two angles, alpha and beta, are defined as opposite angles, and according to this rule, the sum of those two angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we can actually implement the new rule in our drawing. Why? Because in our drawing we have this quadrilateral PQBM that is described by this circle, and those two angles are defined as opposite angles, and according to the rule that I mentioned, the sum of those two opposite angles must be equal to 180 degrees. But the size of this angle is beta, so angle beta plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the two opposite angles of a quadrilateral that is described by a circle. Likewise, those are two opposite angles, so the sum of those two opposite angles must be also equal to 180 degrees. The size of this angle is beta, so angle beta plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees. Therefore this missing angle must be also equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. This is the sum of the two opposite angles inside quadrilateral PQBM. So actually found out that those two angles, this is angle beta and this is angle 180 degrees minus beta. So 180 degrees minus beta plus beta is 180 degrees. So we know that the sum of those two angles is equal to 180 degrees. But those two angles are defined as one-sided interangles. And whenever you have one-sided interangles, the sum of them is 180 degrees, they must be between parallel lines. That is to say, QB is parallel to PM. QB is parallel to PM according to Rule 18. So I'll read Rule 18 quickly. According to Rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between two parallel lines. in the drawing we have line A, this is line A, and this is line B. This is the red line C, intersects with those two lines A and B, those 2 points, and those are angles alpha and beta. Angles alpha and beta are defined as one-sided interangles. And we know that the sum of those 2 angles is equal to 180 degrees. That is to say, we know that angle alpha plus beta is equal to 180 degrees. So that is to say, the sum of two one-sided interangles is equal to 180 degrees. And therefore, according to this rule 18, they must be located between parallel lines. That is to say, line A is parallel to line B. So whenever you have 2 one-sided interangles that the sum of them is equal to 180 degrees, they must be located between parallel lines. We have already implemented rule 18 in our drawing. Why? Because in our drawing we have those 2 one-sided interangles that the sum of them is equal to 180 degrees. Therefore, those 2 one-sided interangles must be located between parallel lines. That is to say, QB is parallel to PM. So QB is parallel to PM according to rule 18. In the next step, I'll copy again this semicircle with the diameter PM, and we will continue to analyze this semicircle. So here this is the semicircle with the diameter PM that I copied from the original drawing. We join points O and Q together by a straight line. Point O is the center of this semicircle, point Q is the point of the semicircle itself, therefore Q is the radius of this semicircle, that is equal to 15 units in its length. Likewise, we join points O and B together by a straight line. OB is of course the radius of this semicircle, that is equal to 15 units in its length. We already found out that according to rule 18, QB is parallel to PM. So write it down, QB is parallel to PM according to rule 18. Those 2 angles are defined as alternating angles, and they are located between the parallel lines QB and PM. And we know that QB is parallel to PM according to rule 18. So those 2 alternating angles are located between the parallel lines QB and PM. And therefore they must be equal to each other in their sizes. So if this angle is alpha, then this angle must be also equal to alpha. So I please click here on rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B. In addition, we have those two angles, alpha and beta, are defined as alternating angles, and according to this rule 15, alternating angles that are located between parallel lines are equal to each other. That is to say, alpha equals to beta. So we have already implemented rule 15 in our drawing. In our drawing, QB is parallel to PM, and those two angles are located between the parallel lines QB and PM, and therefore, according to rule 15, they are equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, because of the fact that according to rule 15, they are equal to each other. Okay? So in the next step, I will copy, actually, this is triangle POQ, again triangle POQ, and this is triangle QOB. So I will present you the law of cosines, and we will implement the law of cosines in this green triangle POQ, and in this white triangle QOB. The law of cosines is true in any triangle. So actually, this is triangle ABC that could be any triangle. In this triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is angle theta. In this triangle ABC, the following equation is true: that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Repeat again, in this triangle ABC, the following equation is true: that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, we will implement the law of cosines in triangle PQO. So copy triangle PQO, and then you implement the law of cosines in the great triangle PQO. This is triangle PQO. So copy it in the new page, and implement the law of cosines in this great triangle PQO. side PQ equals to 10 units length, the side QO equals to 15 units length. This is angle alpha, and side PO equals to 15 units in its length. So actually, this is the grand triangle PQO that I call it from this drawing. So in the next step, we'll implement the law of cosines in this triangle PQO. This will be equation 1. So according to the law of cosines in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Repeat again, in this triangle PQO, according to the law of cosines, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I'll copy this triangle QOB in the new page. In this page, we implement the law of cosines in this triangle QOB. Okay, this is triangle QOB, the quote from this drawing. So we implement the law of cosines in this triangle QOB. This is angle alpha. According to the law of cosines in this triangle QOB, cosine alpha equals to x squared plus 15 square minus 15 square over 15 square plus x square. And again, in this triangle QOB, according to the law of cosine, cosine alpha equals to 15 square plus x square minus 15 square over 15 square plus x square. So we have here two different equations for cosine alpha. So in the next step, we'll create equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared divided by 15 squared plus x squared. So this is equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Here we have 15 squared plus x squared minus 15 squared over 2 times 15 times x. It is over 2 times 15 times x. Okay, I made a mistake. We have to divide it by over 2 times 15 times x. Okay? 2 times 15 times x. We have 2 times 15 times x. Okay? So we focus on the denominator of those two expressions. In both sides of the denominator we have 2 times 15, so 2 times 15 will get cancelled. Here we have 15 squared minus 15 squared is 0, so those two expressions also will get cancelled. So in this side of the equation we're left only with x squared over x. X squared over x is x. So in this side of the equation we're left only with x, while in the other side of the equation we have here 15 squared plus 15 squared minus 10 squared divided by 15. So if we found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. So actually x equals to 15 squared is 225 plus 15 squared is 225. So 225 plus 225 is 450 minus 10 squared. Minus 10 squared is minus 100 divided by 15. So x equals to 450 minus 100 is 350 over 15. So here we divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70, over 15 over 5 is 3. So today we found out that the length of line segment x, the length of line segment qubit is equal to x, is equal to either 70 over 3 units in its length, or in terms of numbers, 70 over 3 is 23 and 30 units. Repeat again, we actually found out that the length of this line segment qubit is equal to x, is equal to either 70 over 3 units, or in terms of numbers, the length of this line segment qubit is equal to x, is equal to 23 and 30 units in its length. Okay, so in the next step, so we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this circle that is inscribed by trapezoid ABCD. A trapezoid is a quadrilateral with one pair of parallel sides. This trapezoid ABCD, side AD is parallel to side BC. Okay, our mission is to find out the area of this circle that is described by this trapezoid ABCD. In addition, we know that this is line segment AM that is equal to A unit in its length. This is line segment MB that is equal to B unit in its length. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of tangent BC with this circle. This point is point Q. Here, you can implement rule 2. Why? Because if you focus on this convex point A, from this convex point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM is A, therefore AP must be also equal to A. Likewise, if you focus on this convex point B, from this convex point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM is B, therefore BQ must be also equal to B units in its length. BQ must be also equal to B units in its length. In the next step, we did the construction, that is to say, from this point A, we do perpendicular on BC. Again, from point A, we do perpendicular on BC. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. Here, by doing this construction, we can do those two angles. They are defined as one-sided interangles and are located between the parallel lines AD and BC. So I want to mention before, in trapezoid ABCD, side AD is parallel to side BC. So we have those two one-sided interangles that are located between the parallel lines AD and BC. And according to rule 17, the sum of two one-sided interangles that are located between the parallel lines is equal to 180 degrees. So the sum of those two one-sided interangles that are located between the parallel lines AD and BC must be equal to 180 degrees. But this is a right angle according to our construction. This is equal to 90 degrees. So 90 degrees plus the size of this missing angle, in total they must be equal to 180 degrees according to rule 17. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we did another construction. That is to say, from this point O, we do perpendicular on AN. Again, from point O, we do perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. By doing this construction, we get here a small quadrilateral APOT. Inside this quadrilateral APOT, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth again, in total it must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth again must be equal to 90 degrees in its size. Likewise, inside this quadrilateral OT and Q, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So we found out that the size of this big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the big angle POQ is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size must be a straight line. Therefore, line segment POQ is a straight line. Line segment POQ is a straight line. If line segment POQ is a straight line, then PQ also must be a straight line. Actually, it doesn't look like a straight line, but because I made an error with the construction, but it should look a straight line. So we know that POQ is a straight line, therefore PQ is also a straight line. PQ is also a straight line. Therefore, shape APQN consists 4 sides. 1, 2, 3, 4. Okay, again. Shape APQN consists of 4 sides. Therefore, shape APQN is a quadrilateral. Shape APQN is a quadrilateral. And we have already found out that in quadrilateral APQN we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side NQ. But AP is A, therefore the opposite side NQ must be also equal to A units in its length. Likewise, according to the sum rule, in the sum rectangle APQN, side PQ must be also equal to the opposite side AN. But PQ is x plus x, that is 2x, therefore AN must be also equal to 2x units in its length. What is the length of the missing line segment NB? Or BN? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ, BQ is B, minus NQ, NQ is A. So in total, BN equals to B minus A units in its length. AB equals to A plus B, and AN equals to 2x. So in the next step, I combine the right triangle A and B with the new page and implemented the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle A and B that are coming from the original domain. In this right triangle A and B, according to the Pythagoras theorem, AB square equals to AN square plus BN square. AB is A plus B, therefore AB square is A plus B square, and it is equal to AN square plus BN square. AN is 2x, therefore AN square is 2x squared, that is 4x squared, plus BN square. BN is A minus B, therefore BN square is A minus B square. So in total, we have found out that A plus B square equals to 4x squared plus A minus B square. Here we open the brackets on both sides of this equation, and finally found out that A plus B square equals to A square plus B square plus 2 times A times B, and it is equal to 4x squared plus A minus B square. A minus B square equals to A square plus B square plus 2 times A times B. Here we have A square on both sides of the equation, so A square will get cancelled, and we also have B square on both sides of the equation, so B square also will get cancelled. After cancelling those two expressions, in this side of the equation we left only with 2AB, in the other side of the equation we left with 4x squared minus 2ab. So in total we found out that 2ab equals to 4x squared minus 2ab. Here we added 2ab to this equation, and finally found out that 2ab plus 2ab is 4ab, so 4ab equals to 4x squared. So here we divided this equation by 4, and finally found out that 4ab over 4 is ab, and 4x squared over 4 is x squared. So in total we found out that x squared equals to AB equals to x squared. Our mission is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. So the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So total the area of our circle must be equal to pi x squared. But we already found out that x squared equals to ab. Therefore we substitute x squared here by ab. So total the area of our circle equals to pi times ab square roots. And again we found out that the area of this circle is equal to pi times AB square root. So finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. Our mission in the second question is to find out the length of this standard of this 9 cm QB or chord QB is equal to x. We have to find out the value of x. So in the drawing, the original drawing, we had here a semicircle. AB, that is the diameter of this semicircle, equals to 30 units in itself. Chord AP or chord PA equals to 10 units in itself. Chord PQ also equals to 10 units in itself. And our mission is to find out the length of chord QB or 9 cm QB that is equal to x. We have to find out the value of x. So in the first step, we define the center of this semicircle. This point is point O. We know that the diameter AB of this semicircle is 30, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. Point O is the center of this semicircle, point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle, that is equal to 15. Likewise, OB is also the radius of this semicircle, that is equal to 15. We join points O and P together by straight line. Point O is the center of this semicircle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle, that is equal to 15. In the next step, we completed this semicircle to a circle, and we extended the radius PO until it touches this circle at this point. We define the touching point of the extended radius PO with this circle. This point is point M. In the next step, OM is of course the radius of this circle, that is equals to 15. We join points M and B together by straight line. In the next step, we prove that before that, we have those two vertex angles, they are equal to each other. Okay, we have the rule that vertex angles are equal to each other, so those two vertex angles are equal to each other. In the next step, we prove that this triangle PNO can go into this triangle OBN. So why those two triangles can go into each other? First of all, side PO or triangle APO is equal to side OM or triangle OMB. They are both the area of the circle, therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. And finally, side OA of triangle APO is equal to side OB of triangle OBL. They are both the area of the circle, therefore they are equal to each other. So we prove that those two triangles can go into each other according to side angle side rule. That is to say, we prove that those two sides and the angle that included between those two sides in triangle APO are correspondingly equal to those two sides and the angle that is included between those two sides in triangle MBO. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side AP is equal to side MB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides AP and MB must be also equal to each other. Repeating again, we will derive that from the fact that those two triangles can go into each other, that side AP equals to side MB. But it is given us a question that AP equals to 10. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB. We will derive that MB also equals to 10 units in its length. This is side MB that is equal to 10 units in its length. PM, chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PM is the diameter of this circle. In the next step, I copied this semicircle with the diameter PM and we analyze this semicircle. So actually, this is the semicircle with the diameter PM that I copied from the original drawing. Point O is the center of this semicircle. QP equals to 10, BM equals to 10, and we extended line segment PQ, line segment MB by side line until they intersect with each other at this point, point E. And we have the rule that if you extend two line segments that are equal to each other in their lengths, the new line segments must be also equal to each other. We extended PQ and MB, and we got the new line segment that is PE and ME. And according to the new rule, PE must be also equal to ME. Again, according to the new rule, PE must be also equal to ME. The two line segments, the two new line segments must be also equal to each other. So, by doing this construction, we get the deal. Triangle PEM. In triangle PEM, side PE equals to side EM, therefore triangle PEM is an isosceles triangle. Those two angles are equal to each other according to the rule that in front of equal sides in the triangle there are equal angles. In front of this side PE we have this angle, in front of this side EM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to each other, to beta, because they are equal to each other according to the rule that I mentioned. So if we found out that those two angles are both equal to beta, in the next step we completed this semicircle to a circle, and actually we have here quadrilateral PQBM that is inscribed by this circle. And we have the rule that any quadrilateral that is inscribed by a circle, the sum of its two opposite angles is equal to 180 degrees. So because of the fact that this quadrilateral PQBM is inscribed by this circle, the sum of its two opposite angles must be equal to 180 degrees. That is to say, the sum of those two opposite angles must be equal to 180 degrees. But this angle equals to beta. So beta plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles, the sum of the opposite angles in a quadrilateral that is inscribed by a circle. Likewise, the sum of those two opposite angles must be also equal to 180 degrees according to the same rule. But this angle is beta, so angle beta plus this missing angle in total must be equal to 180 degrees. So therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in a quadrilateral that is inscribed by a circle. So in total we found out that this angle equals to beta and this angle equals to 180 degrees minus beta. 180 degrees minus beta plus beta is 180 degrees. So the sum of those two one-sided interangles is equal to 180 degrees. And therefore, according to rule 18, whenever we have the sum of two one-sided interangles that is equal to 180 degrees, there must be between parallel lines. That is to say, QB must be parallel to PM. Again, according to rule 18, because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, those two one-sided interangles must be between parallel lines. That is to say, QB is parallel to PM according to rule 18. In the next step, I copied this semicircle with the diameter PM in a new page, and we continue to analyze this semicircle. Actually, this is the semicircle with the diameter PM. Point O is the center of this circle. OP equals to OM equals to OB equals to OQ. They are both the radius of the circle. This equals to 15 units in length. PQ equals to 10 and MB equals to 10. We have already found out that QB is parallel to PM. Those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. And therefore, according to rule 15, the sum of two alternating angles that are located between parallel lines is, alternating angles between parallel lines are equal to each other. Those two alternating angles that are located between the parallel lines QB and PM must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, because they are equal to each other according to rule 15. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this green triangle PQO and in this white triangle, triangle QOB. So what is the law of cosines? The law of cosines is drawn in any triangle. So actually, this is triangle ABC, that could be any triangle. This triangle ABC, side AB equals to A units in itself, side AC equals to B units in itself. This is side BC, that is equals to C units in itself. This is angle theta. This triangle ABC, that could be any triangle. Cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. In the next step, we implemented this law, the law of cosines, in the green triangle, triangle PQO. So actually, this is the green triangle PQO that according to the original drawing, this is angle alpha. According to the law of cosines, in this triangle, triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Repeat again, according to the law of cosines, in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I copied the white triangle PQO here, and we implemented the law of cosines in this white triangle QBO. So this is the white triangle QBO that I copied from page 3. This triangle QBO, this is angle alpha. So according to the law of cosines, in this triangle QBO, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. And repeat again, according to the law of cosines, in this white triangle QBO, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Okay? So we have two different equations for cosine alpha. Therefore, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Repeat again, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 square minus 15 square over 2 times 15 times x. If you focus on the denominator of those two expressions, in both denominators, we have 2 times 15. So 2 times 15 will get cancelled. So in this side of the equation we have 15 square minus 15 square is 0. So the numerator of this expression will have to leave with x squared over x. X squared over x is x. So in total, in this side of the equation we have to leave with x. While in the other side of the equation we have 15 squared plus 15 squared minus 10 squared over 15. Again, x equals to 15 squared plus 15 squared minus 10 squared over 15. 15 squared is 225, so 225 plus 225 is 450, minus 10 squared, that is minus 100 over 15. So in total we can find out that x equals to 450 minus 100 over 15. 450 minus 100 is 350. So in total x equals to 350 over 15. Here we divided both the numerator and the denominator of this number by 5, and we found out that 350 over 5 is 70, and 15 over 5 is 3. So in total we found out that the length of line segment qubit that is equal to x, it is equal to either 70 over 3 units in its length, or the length of qubit that is equal to x is, in terms of numbers, it is equal to 23 and 3rd units in its length. I repeat again, we actually found out that the length of this line segment qubit that is equal to x, it is equal to either 70 over 3 units in its length, or in terms of numbers, the length of this line segment qubit that is equal to x is equal to 23 and 3rd units in its length. Okay, thank you very much.